we've defined the determinant for a matrix, for a square matrix, but we haven't for a linear transformation. And we actually have a good reason to think that there is no good definition for the determinant of a linear transformation in general, even if your linear transformation is going between two spaces that have the same dimension. So the two spaces would have to have the same dimension for to have any hope of having a determinant, because to have a determinant you'd need the matrix for the transformation to be square, and that is only going to be possible if the dimensions of the input and the output spaces are the same. But if they're actually different subspaces, then we should have no hope of having a determinant, because how we defined a matrix is we had this coordinate, if you choose bases for v and for w, we have these coordinate transformations that go like this, and so we'd have Rn and Rn, and the matrix is the matrix for this composition of linear transformations. Well, if v and w are different subspaces, we can change the basis for w without affecting the basis for v, and in that case, that would change the determinant of this of the matrix that you get. If you doubled the length of all of your basis vectors, it would double, I think, the determinant of the resulting matrix. So in general, there's no hope for defining the determinant of a linear transformation. But there is a special case. If your linear transformation has as its domain in the range the exact same subspace, so not just isomorphic spaces, but literally the exact same space, then we can define a determinant. So to do that, first let's pick a coordinate system, or pick a basis for v. So let's choose a basis, and we're going to need another basis, so let's call this one b1. Let's say it's v1 through vn. Okay, so this is a basis for v. Then to define the determinant of the linear transformation, we can just define that to be the determinant of the matrix that represents T relative to this basis. So A sub b1 is the matrix for this transformation relative to the basis b1. And this makes sense because we have Rn, we have our inverse coordinate transform that goes to v, then our linear transformation that goes to v, and the key thing here is we aren't choosing a basis for two different spaces like we were up here. Once we choose a basis for the domain space, we automatically have a basis for the range space because it is the same space. So by choosing one basis, we've actually chosen both bases. Now, we have some hope of this definition making sense because if we change the basis for one of these, we're changing the basis for both of them. So there's some hope that, if both of them change, they sort of change together in a way that makes the determinant come out the same. So to see if this definition actually makes sense, we need to check if we used a different basis, would we get the same determinant? All right. So to work that out, let's say that B2 is another basis for V. Okay, so for a vector in V, since we have two different bases, there are going to be lots of coordinates flying around. So for a vector in V, in the past I've used this notation for coordinates, but I'm going to use this notation. So just a subscript with sort of vertical bars around it. So for coordinates, relative to this basis, this is the notation that I'm going to use. And for coordinates relative to the second basis for a vector, that's just going to be the same thing but with b2 down in this subscript. Okay. Now, when we were talking about the coordinates, we saw that there is, so to turn coordinates relative to one basis into coordinates relative to a second basis, there's actually a matrix that will do that, and I'm going to call this CB2B1. So this is the matrix that if you have coordinates relative to B1, you multiply by this matrix, you get coordinates relative to B2. Since B1 and B2 are bases, this matrix is guaranteed to be invertible, and its inverse goes the other way. So the inverse of this usually gets called a transition matrix. So the inverse of this transition matrix takes coordinates for B2 and turns them into coordinates for B1. Okay, now what we're going to do is figure out, so we have this matrix relative to the first basis. What we're going to do is figure out the matrix for this linear transformation relative to the other basis, B2. Okay, so we have this matrix for the linear transformation relative to B1. But what does that mean? What that means is if you start with coordinates relative to the first basis and you multiply by this matrix, what you get are coordinates relative to the first basis of the linear transformation applied to the vector. Okay, so this is what it means for this matrix to be the matrix for this linear transformation. All right, well, notice that what we have here are coordinates relative to the first basis. So if we multiplied by our transition matrix, we would get coordinates relative to our second basis. So let's multiply on the left on both sides by this transition matrix. So we get C sub B2 B1 relative times A sub B1 times coordinates relative to B1 equals C B2 B1 times coordinates for T applied to V relative to B1. Okay, but now notice on the right-hand side we have some coordinates relative to B1 times our transition matrix. And the result of that is coordinates relative to B2 for T of V. Okay? Fair enough. Unfortunately, the way that it stands right now, this doesn't tell us anything about a matrix for the transformation relative to B2 because these coordinates over here on the left-hand side aren't with respect to B2, they're relative to B1. But look, over here, we have a formula for the coordinates of V relative to B2. We have a formula for the coordinates of V relative to B1 in terms of B2, right? So we can put that down here. So we get C B2 B1, so this transition matrix that translates between coordinates in the relative to the different bases, times A B1, and then this part right here turns into the inverse of our transition matrix times the coordinates for V relative to B2, and this whole mess is equal to coordinates relative to B2 of T of V. Okay, now look, here we have coordinates for a vector, we multiply by a matrix, and we get coordinates for the result of the transform. And critically, these coordinates are relative to the same basis, right? This means that this matrix, CB2B1 times A relative to B1 times the inverse of CB2B1 is the matrix for the linear transformation relative to the second basis, right? This is the matrix that takes coordinates for the input to coordinates for the output. So this is the matrix for the linear transformation t relative to our second basis. So what is the determinant of this matrix? Well, the matrix relative to B2 is our transition matrix times the matrix relative to B1 times the inverse of our transition matrix. But the determinant of a product is the product of the determinants, so this is the determinant of our transition matrix times the determinant of A relative to B1 times the determinant of the inverse of our transition matrix. Okay. But the determinant of an inverse is the reciprocal of the determinant for the original matrix. So this last piece actually cancels the first piece, and we just get the determinant of A relative to the first basis. Okay, so what this is saying, right, zoom out, big picture here, what this is saying is that the determinant of a matrix relative to a basis is the same no matter which basis you choose. And so we can make this definition that the determinant of a linear transformation is just the determinant of its matrix relative to any basis, because no matter which basis you choose, this determinant will always come out to be the same. So this definition makes sense, and if we have a linear transformation from one subspace to another, there is such a thing as the determinant of that linear transformation.